Hey, welcome back to Calculus. In this last section of Chapter 5, we're going to talk about a technique of computing indefinite integrals, that is antiderivatives, by a method called substitution. We'll focus on indefinite integrals in this first part of it, and then we'll turn our attention towards definite integrals, that is integrals with limits of integration, in the second day. Okay, so I want to show you what I mean by this substitution method. Sometimes people will refer to this as U substitution, because we're going to make a variable change, and it's very typical for the name of that variable to be u. It doesn't have to be, but if you hear people speaking about u substitutions or just substitutions in general, they mean the same technique. All right, so I want to kind of motivate the technique with a warm-up problem here. The warm-up problem is to compute the derivative of this exponential. It's a chain rule problem. You have to take the derivative of that outside function, that is the derivative of the exponential, evaluate it at the inside, and then multiply that by the derivative of the inside. Okay, in this case, the derivative of the inside ends up being 2x. And if I rearrange that nicely, I can write my answer as 2x times e to the x squared plus 1. Good. So why do this as a warm-up for this substitution method? Well, the substitution method is really sort of a method of doing the chain rule backwards. Yeah. What if I walked in and said, hey, I'd like to find an antiderivative for a function like 2x times e to the x squared plus 1. It's not in my list of functions that I recognize as the derivative of something. So I need some technique. I need some method for finding this antiderivative. Yeah. And how can we analyze it? Well, it's got an exponential in it. Exponentials are certainly antiderivatives of themselves. But what about this part? What about this 2x? You might notice in looking at it that, and you certainly should notice based on the computation that we just did, that this 2x is in fact the derivative of the exponential function's exponent, x squared plus 1 in this case. So you might look at this and say, well, this 2x is laying around because of a chain rule. The chain rule happened. In fact, we just saw it happen. That's exactly why that 2x. What's that 2x the derivative of? It's the derivative of the exponent. It was the derivative of the inside function. So I'm just going to kind of use this technique on the fly here. What we're going to do when we look at these things is we're going to, if we recognize that some chain rule happened, I'm going to let a new variable called u equal what I think that inside function was. In this case, it's 2x squared plus 1. And then I'm going to compute the derivative of u, but I'm going to compute that derivative in differential form. I'm going to write the differential, like from the linearization section. Du is, well, 2x is the derivative of x squared plus 1, and I multiply that by dx in the differential form. All right? So all of this is motivated by that example above. So now if I start substituting this stuff, I'm going to rewrite this integral. I'm going to rewrite this integral in the new variable u. So let me use some highlighting to show you. U is going to go right there in the formula, right? U is x squared plus 1. So my goal is to rewrite this thing without any x's in it, so that e to the x squared plus 1 becomes e to the u. And then what's left in this integral? Well, I have this 2x times dx. I know they're not right next to each other, but they don't have to be. It's still 2x times dx. And our differential expression says that 2x times dx is replaced with du. Okay, so after I do that, this equality is now valid because all expressions have been replaced in the new variable. I still have an antiderivative to do, but this antiderivative is much more elementary, right? The antiderivative of e to the u is itself, well, plus a constant, because this is a general antiderivative. And then my last step is to remember that in the original variable, u was equal to x squared plus 1. So I'm just going to solve, or replace that rather. Okay, so that's how I might derive that the antiderivative of 2x times e to the x squared plus 1 is e to the x squared plus 1. That is how I might do the chain rule in reverse. What do I mean by the chain rule in reverse? I mean that we identified what we think is our inside function right there, yeah, and then we took its derivative and algebraically manipulated the integral to replace those things in terms of that new variable where we could successfully anti-differentiate. Cool. Okay, well, let's try several. Just like in your homework, I'm gonna ask you. The best possible thing that you could do for yourself as we're winding up our course this week is to do as many of the substitution problems in the book as possible. You'll notice that the homework assignment looks a little large. I did something do one through something big, odd problems. Well, you just have to practice this. Unlike the section 4.7 optimization problems, these things are not long and involved. They're kind of quick, but the algebraic sort of motions is what you need to get used to. Before I started my long tirade there, I was going to say that the first few problems, like in the book, I'm going to suggest what U is, and then soon I'll leave it up to you to decide that. It's never clear when you're first looking at one of these things. You gain the ability to make this substitution by experience. So in this case, I want to find the antiderivative of that expression that you're looking at, and I've suggested to let U equal what's under the square root. Okay, so if I compute the derivative, always in differential form, I get 3x squared. My motivation for U was the fact that its derivative of what's under the square root is also a factor of the integrand. That's kind of a clue for what to look for. So 3x squared dx, and now I'm going to just start replacing things. I always replace the thing that I substituted U for first. And in this integral, that's right there. So it's the square root, but I'm going to integrate this thing. So I'm going to write that square root as a 1/2 power. Okay, maybe it'll be helpful if I put over here what's equal to what. So I'm replacing U with that x cubed plus 5. And then I ask myself what's left. Well, 3x squared times dx. So I come down here to my differential equation. I'm always going to look there for the what's left part, and I see that 3x squared dx can be swapped for du. Okay, so I do it. I've algebraically accounted for everything. That's why this equality is valid, and I've also rewritten this integral, and it is an antiderivative I can do. So that's the kind of general spirit of these problems, is you take an integral in one variable and via substitution, you rewrite it as an integral in another variable that you can successfully do. So here in this case, I have to add 1 to that exponent and divide by the new exponent and add my constant. And I'm not done just because I want to answer in the original variable. My answer should be in terms of x in this case. The original variable was an x. So the equation that takes you between U and X is your very first substitution. So I'm just going to write here 2/3, and then I have x cubed plus 5 to the 3/2. Okay, so there's my proposed antiderivative for the original function, and I can always check it. I highly recommend you do this as well. If you take the derivative of 2/3 times x cubed plus 5 to the 3/2, well, plus any constant, you're going to have to use the chain rule. And in using that chain rule, it's going to make the substitution make more sense. 2/3 is a constant. It stays out front. Differentiating a power, you bring that power down, take the thing that was in there and write it to the power that's 1 less, and then multiply by the derivative of the inside, which in this case is 3x squared, well, plus 0. The derivative of the constant is 0. Okay, well, 2/3 times 3/2 is 1, and you can see immediately that we get 3x squared. I'm going to write the 1/2 power as a square root, so it matches. It's precisely the function that we wanted to find the antiderivative of. All right, so you can always check an antiderivative problem. You never have to get one wrong if you're willing to differentiate it, and you can differentiate correctly. And again, I think this is useful because maybe this is just me, but in doing this, I sort of understood this substitution better. I understand why x cubed plus 5 was the thing to take and make U, because that was the inside function. Okay, let's just try to do lots more here. So I've got a third example. Here I'm not telling you what U is. It's a great chance for you to stop the video and do this by yourself if you've already caught on. In general, you're looking for some inside function in the sense that its derivative is also in there. Well, if I let U equal x squared plus 6, or excuse me, x to the 6th plus 11, pardon me, then its derivative is 6x to the 5th. So that motivates the substitution let's let u equal that denominator. Okay, its derivative, we just said it, it's 6x to the 5th dx, differential notation. And then should I color code one more of these things? I'm looking to see, first of all, what is my u? Well, it's x to the 6 plus 11, so that's right there. So I'll put that in as 1 over u. And then once I do that, I ask myself, what's left? Well, in this case, it's 6x to the 5th dx, and that's exactly equal to du. Okay, so after making those substitutions, everything's accounted for, and now I have to ask myself, do I know an antiderivative for 1 over u du? Sure I do. It's the natural log. The natural log of the absolute value of u is the general antiderivative for that, and then the last thing to do is to replace it. I'm going to leave the differentiation check to you, so this video doesn't get too long, but you can check that. And the derivative of that natural log is, in fact, 6x to the 5th over x to the 6th plus 11. Okay? Let's try another one. Stop the video. What do you think we should let u equal? Okay, hopefully you stopped it and answered, but I'm going to let u equal x squared. So du is 2x dx. And now I'm going to start trying my substitution. I like to try to substitute the u variable first. So that's cosine of u. So life is looking good. And then I'm going to go to my what's left color. Well, x dx is left, right? I substituted u equals x squared. That's where that came from. And I'm looking for what's left. And x dx is left. So I go to my differential equation, and be careful, look what I'm highlighting. X dx does not equal du. I see x dx down there, but it doesn't equal du, but I can solve for it. X dx is equal to 1/2 du. Okay, so we have to be honest and replace equals with equals. So what's left is x dx. So I replace that with 1/2 du. All right, so now we're accounted for. Everything has been equal. But that 1/2, I'm just going to bring this over here so I have some more room. 1/2 is a constant. I don't have to put it in that integral. The essence of this problem is integrating the cosine function. I'll multiply it by 1/2 later. The antiderivative of cosine is sine plus a constant. And since the original variable was in terms of x, so there's my answer. I'll let you check it with differentiation. All right, so maybe at the beginning of the example, it was kind of different than the other ones. My first 3 examples, I would have kind of had the 2 there. And maybe when you saw this example, you went, oh no, there's no 2, it's not gonna work. Well, it still works. It's okay if the derivative of your proposed substitution isn't right by a constant factor, because you can always take that constant factor over, and a constant factor can come out of the integral sign. So it's not a problem if your substitution is sort of not replacing everything up to a constant. You can just sort of solve for what you do, and as long as what's left over, quote unquote, this extra factor is a constant, it can come out front, right? That would be very different if this would have been, say, like x squared, because then in my differential form, I've got no x squared. And to get one, I have to put an x. You won't be able to separate. But if you're just off by a constant, it's not going to be a problem. Cool. Let's try another one. Lots of examples in this lecture. Stop the video and go ahead without me if you can. Here, I'm going to let u equal 3x minus 7. Du in this case is 3 dx. I'm just computing the normal derivative. 3 is the derivative of 3x minus 7, and then I'm writing it in differential form. All right, so I'm going to do this, I think, without the color coding this time. I'm going to write, well, that's u to the 99, and then what's not accounted for? Well, dx. Well, dx is 1/3 of du if I solve my differential form. So that 1/3 du is what replaces my dx. But 1/3 is a constant. So really, the antiderivative that I have to do is u to the 99th. So I should add 1 to that exponent, divide by the new exponent. So we end up getting 1 over 300 times, let me replace u with its expression in x, 3x minus 7 to the 100th. Okay, I'll let you again check. I hope you're checking these. Stop them. This video is not too long. Okay, let's keep going. Stop the video for a second. Can you decide what u is here? The original variable is called theta. It's no problem. When I look at this thing, I see a sine to the 5th, and the derivative of sine is cosine. So this integral, as people say, is just of the form u to the 5th. What do they mean by that? If I let u equal sine, said its derivative is cosine, differential form du is cosine theta d theta. So this is just the integral of u to the 5th du. Cosine theta d theta is just perfect swap for du. The antiderivative of u to the 5th is 1/6 u to the 6th plus a constant. And in terms of the original variable, remember for trig functions, we write this exponent in this kind of exotic location. It's 1/6 sine to the 6th. Nice. The substitution method has kind of rapidly, vastly, expanded the kinds of functions that you can find antiderivatives for. In this first semester of calculus, I'll kind of stick in a comment here. You've learned how to differentiate basically every function you'll ever run into. You can differentiate anything I can. With the differentiation rules, you can take any function assembled in any way and just differentiate it. Anti-differentiation is a very different critter. It's easy for somebody to write down a function that nobody can find an antiderivative for. In fact, the first third of Calc 2, if you're going to take Math 110 or Calc 2 somewhere else, is sort of focused on techniques of anti-differentiation. And even after 5-6 weeks of studying techniques, it's still the case that someone could easily write down an antiderivative that we can't do. In general, anti-differentiation is much more difficult than differentiation is. But this substitution method is certainly pretty nice. Let's try a couple more here. Stop the video and see if you can make this choice on your own. When I look at something, if it's a fraction, I like to ask myself, is the derivative of the denominator up to a constant the numerator? Because if it is, I'll let u equal the denominator. And in this particular case, if u is e to the t plus 1, then du is e to the t dt. And that's precisely the numerator. So this integral, I'm going a little faster now, has the form 1 over u du. It's just like the one before. The essence of it is a logarithm. It's the natural log. Yeah, so you can compare this to previous example where we had a 1 over u du. They both have the same form, derivative of something over the something. And when that's the case, the antiderivative for it is the natural log. In this case, the something is e to the t plus 1. Above, I forget what it was, x to the 6th plus something. Nice. All right, so let's kind of summarize this method. The substitution rule. If you're given some integral, look at this form. I'm going to try to use the same color coding that I was before. G is the inside function. So I let u equal g of x. I should write that here. I let this. It's a choice. People don't tell it to me. And then I compute the derivative. And then I look in the integral and see what's left. Well, g of x times dx is left. G prime of x times dx. Okay, so that's equal to du. So that integral just equals, I replace the g prime of x dx with du. I replace the g of x with u, and I transform the integral into u. It's still not done, but hopefully you get an integral that you can do. So you hope you can find this antiderivative, just like in our above examples. So substitution by itself just trades one integral for another. But hopefully the other one is doable. Then you do it and you substitute back. Okay, I kind of threw in, I didn't even really call it an example. This is a special case that comes up a lot. So I threw it in here when the inside function is just a constant times the variable and an exponential. So the formula I've written there, the antiderivative of e, here a is a constant. I should write it. It doesn't depend on t. The antiderivative of e to the at, this is an important antiderivative in lots of applications. It's 1 over a e to the at. And you can see that with this substitution. I wrote out the details so we don't have to go slow. But if you just let u equal at, well then du is a dt. So dt is 1 over a du. So when you replace all of that, I'm going to leave the details to you. You end up just getting 1 over a times the integral of e to the u du. So that you get that antiderivative. Okay, so you check out the details here. I'm just kind of putting it here as a special case. It comes up a lot. In particular, like if a was 1 over 2 pi. Sometimes it's kind of nice if you don't have to stop and spend a lot of mental energy on an antiderivative like this. You guys have seen exponential growth and decay problems and so on, where you're always looking at e to the number times something. And if you want to know its antiderivative, it's sort of a nice formula. Okay, so for our last example, let's do something that's kind of a little tricky. You should stop this and think about it. It's never obvious at the first glance, but just like with logarithms, if I see an exponential expression, I try to let u equal the exponent. It won't always work, but it's a good bet. So here, the derivative, maybe if I leave it in radical notation, some of you guys like this formula, it's 1 over 2 times the square root of x dx. So if I go to do my replacing, let me do my color coding here. So square root of x is u, yeah? So I'm going to write this as well, e to the u. That takes care of that part. And then what's left? Well, what's left is 1 over root x times dx. I see a 1 over root x times dx, and I can solve for it. It's 2 du. So if I replace, oops, that 1 over square root x dx with 2 du, then I've accounted for everything equally. Okay, 2 is a constant, so I can pull it out. So this is just an integral of e to the u. The antiderivative is 2e to the u plus a constant, replacing everything in terms of x. Okay, I hope those examples were illustrative. There's more examples you can read in your book. We'll worry about definite integrals next time, but in the meantime, practice, 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 practice this. Okay, thanks for